Thank you so much for joining us here at Supercomputing 2024 here in Atlanta, Georgia. We're so happy that you're here. Thank you for escaping the rain and joining us here in our Intel booth theater. We're having presentations that are happening throughout the day, every half hour. Wonderful presentations with people, the movers and shakers that are in the field that can tell you more about what Intel is doing with our partners to create a better space. Right now, our next presentation is about the overview of open platform programming methods for exascale computing, coming to you from the University of Bristol. Let's give a warm welcome to Dr. Tom Deakin.
Great, thank you very much for your introduction. I would like to begin today by telling you a short story, and it's a story that you know very well, and it's that of the young postdoc armed with their laptop, trying to follow this yellow brick road all the way to Oz to try and understand about how they can get this performance portable code. They're dealing with this massive million-line code piece of application, and they only want to write it once, right? It's too hard to be able to port your code to lots of different models to different machines, and there's the different accelerators that you might have access to. And so this hopefully feels like a very familiar story, and it's something that I've been thinking about for a long time. So this was a paper I published at one of the workshops in supercomputing 4 years ago now, at the P3 HPC workshop. It's the workshop where we all get together to talk about performance portability and how we can write applications once that run on different architectures. And part of this is by developing these parallel programming models to enable to do that. And back then, we weren't quite at exascale. Back in 2020, we were still on our way to exascale. And this title I had was about the challenges that we face on how we actually understand how applications can be performance portable. And the reason we care about this is because we have this deluge of different types of processors, CPUs, we have GPUs, we have AI accelerators, both from Intel and other vendors, right? And if we're writing applications, then those applications have to last a long, long time. We might buy supercomputers on a cadence of every 3 to 5 years, maybe a little more. But those applications have lasted decades, right? Some of the applications that many of the scientists have are 50 plus years old, right? So how does that application manage when they are in this situation, right? They've got all these different processor types raining down on them. How do they write their application so that they know that it's going to get good performance as they migrate from one system to another, try out the latest generation of CPUs and GPUs? The other interesting aspect of this is if we look at the top 500, and this is not up to date. I had to submit my slides a little bit early, but this was from June this year. The top 500 list is a list of the world's largest supercomputers. And what was very interesting is if you, rather than count order the list by, say, which is the most powerful, but you just explore the list and say, well, how many of them actually have accelerators right now? And how many of them don't? And obviously, most of the performance, if you bias by performance, you get the best performance from the accelerators on the HPL benchmark. But if you think about the number of machines that do not have accelerators, it's like 2/3 of the machine. So if you take any given scientist, right, that girl who's on her way down the yellow brick road to Oz, what's the chances of having an accelerated system versus getting onto a large-scale GPU system? So we really care about an application that maybe needs to run really well on CPUs, but also run really well on GPUs as that institute maybe gets a larger and larger compute. At the same time, though, the list also captures the kind of diversity in those CPUs in the system, and we see that lots and lots of them are from all different kind of vendors. The bulk is still, at the time, was still Intel CPUs in the top 500 list back in June. But we still have this diversity in the host architecture, diversity in the accelerated architecture, and this puts a real pressure on the applications to try and understand the kind of performance that they need to get and how they can make sure their application is going to be ready to last a very long time. What I find very interesting actually about this left-hand side of the list is GPUs first entered the top 500 list with a machine in 2012. So we're kind of over a decade on, and still the GPU technology is filtering slowly down the list. So obviously, as I said, most of the largest machines, and to get the best performance, the GPU accelerators provide that. But it's taking us, a community, a very long time for us to adapt our codes to kind of get towards GPUs. And this is where I think those parallel programming models that support the whole range of CPU and GPU architectures are kind of vital to try and accelerate this kind of adoption and to make sure that this can happen. This is typical in some sense of the top 500 list. The brand new kind of architectures and innovations happens at the top of the list, and then they trickle down to the smaller and smaller systems. But for some reason, the accelerator one is taking quite a long time. And my personal opinion is I think it's on the software side. Getting softwares ready for accelerators and keeping them running on as the accelerators are kind of developing underneath is a very interesting challenge. So what do we do, right? We have this this code. You might have been written by some old professor there, and you're the young scientist trying to go, and they're asking the good witch here about which way to go. How do I solve this problem? How do I write my application that gets good performance that's going to last a long time? I asked generative AI to make these images, and I have no idea what this creepy figure on the left-hand side is. I put in a prompt that was like, yeah, I'm asking, my young postdoc, I'm asking for advice, from the good witch about how I should, which parallel programming model should I use? And for some reason, there's this kind of crazy person in the background. It's very kind of odd. But yeah, emphasizing the challenges of all these different processes that are in our ecosystem that we have to deal with. So a lot of my research is trying to really understand and characterize this notion of performance portability. In Bristol, we came up with this definition and collaborating with colleagues from Intel, people like John Pennycook. And we came up with this definition here that a code is performance portable if we can get a similar fraction of peak performance on a range of different target architectures. We want that range to be as broad as possible. In Bristol, we basically try and every CPU and GPU from everybody as far as we can go. This is a high performance computing conference, right? So the similar fraction of peak hardware performance needs to be a good fraction of peak performance, right? We want to get good performance, so we want to get a high fraction of peak performance. What I'm most interested in terms of the performance portability is this consistency. I want to make sure I get great performance from a single application across all the different target architectures that I might try, and ideally, as far as possible, from a single code base. Specialization is a reality of life. We are always going to have to optimize and specialize our codes. But how far can we push this? How far can we get with just a single code base that runs everywhere? So these are the sort of experiments that we do. This takes a very simple application. It was a stream triad from my Babel stream benchmark. It's basically like a DAXP, just a vector addition. And on the left-hand side, we tried a whole bunch of different processors, CPUs and GPUs from basically everybody at the time we did this study 3 or 4 years ago. And we implemented this code in 6 or more different parallel programming models. Each of them are able to target, ideally, as many of these as possible. What the results are showing is that fraction of peak performance. So the benchmark reports how fast it went. And we asked the vendors, we looked at the tech sheets that they provide, how much memory bandwidth do you provide on your processor? And we take the ratio of that, and that's the percentage that is presented here. I hate to pick on some models, but you'll see some models only support one particular class of architecture. And you see that where, like, for example, the CUDA model only supports NVIDIA GPUs, so we can't run it on CPUs or GPUs from anyone else. But where it does run on their platforms, then it obviously gets great performance. What I'm interested in making sure that with these parallel programming models that the columns are complete, that the columns we're able to run our code everywhere, the code is portable to start with, and then the consistency of that code means we get good performance in all the things we try. Now, I will just caveat this figure and say this was done 4 years ago, and everybody's software stacks has improved enormously in those 4 years. So if we ran this study again, obviously we would expect some of these numbers to improve in particular places on the graph. Like, for example, the SYCL performance we know has got a lot better in the last few years. But running these benchmarking studies is really hard. I estimated this is about 1.5 FTEs, 18 months worth of work to produce one of these studies. We parallelize it, otherwise it's impossible to do. But it takes around, we reckon it was 18 months worth of people time just to kind of do this kind of exhaustive study. We had loads of people on this study, which meant we could do it in time, just to capture this snapshot 4 years ago of what performance portability looked like. So all of these parallel programming models essentially define a view of the world in these 3 main abstraction categories. The first is device discovery and control. You no longer have one type of processor that's in your system anymore, so you have to understand from a programmatic way, what devices do I have? How do I program? How do I choose between the CPU and the GPU, say? How do I offload work from from my application to each of those different accelerators. So they all provide some different kind of abstraction for doing this. OpenMP provides the target directive that uses tasks for this and the device clause. SYCL provides a queue. Likewise with OpenCL, CUDA provides a stream, right? They all provide a way of finding out what processes I have and for how do I offload work to do them. The second abstraction that all of these models provide is essentially where does my data live? These systems not only have heterogeneous compute, but they have discrete memory spaces associated with them. Many of those processes might provide some kind of unified shared memory to make this bit very easy, so you don't have to think about this as an application developer, but many times you really need the control to understand where your data is and to decide whether it lives in the CPU memory or whether it lives in the GPU memory. So you need some APIs, you need some control of that in your parallel programming model. And finally, on the right-hand side there, you need some way of expressing the compute. You need to express the parallelism in your compute. It's by writing parallel kernels, by writing parallel loops, all these sorts of things. And each of the different models does it slightly differently, but they all provide some abstraction for doing this. So in many ways, which of the models you pick, they're all giving you these abstraction and giving you these controls, but with varying levels of controllability. And this is what kind of the nuances between these things, but they're all fundamentally have the same view of a heterogeneous architecture. So what if I write a program that's going to run really well on GPUs, but I also want to run it on a CPU as well, right? And this is what I did. I looked at this a few years ago. This was following that, the journey down the yellow brick road to say, well, I have a CPU system now, but I know my next one is going to be a GPU system. And how can I prepare for my GPU system, but also still get work done on the large scale CPU-only machine that I have now? So this looked at the same application, and I took my GPU code that I wrote for a GPU, but compiled it for a CPU. So I just pretended the CPU was just like a GPU, right? It's just some multi-core provided accelerator. And what was awesome about this is with basically any parallel programming model I picked, I had a couple of compilers that I could use to build my application and run on the CPU with exactly the same performance as I would get if I just hand wrote it, say, in OpenMP only for CPUs. Just a typical shared memory parallelism. On the left-hand side is an Intel x86 Ice Lake CPU on the right-hand side and an AMD x86 Milan CPU. And I have results in this paper for ARM CPUs as well. And the same was true, right? So I can write a program that's GPU focused and just compile it and run it on CPUs and get exactly the same performance as well. But if you think back to that heat map I already showed you that these models get good performance on GPUs as well. So I now am being able to write this performance portable code that gets great performance on CPUs and GPUs, which is really great. So really, this is a call to action, right? We're in the Wizard of Oz, and obviously we meet a lion on the way. And really, the lion in the story asks for courage, right? It's a very scared lion. And this really kind of tries to capture, what do? I have to make a decision today about what parallel programming model I write in. So really, I'm saying embrace that heterogeneity. Try and think about programming the whole system. Think about using the CPUs. Think about using the GPUs. And the heterogeneous nature of these systems. And actually, you can write the same kernels. We've tried simple things and more complicated things too. If we think about processes and accelerated compute, we often see the same benefits of optimizations happen on the CPUs as well. So kind of embrace this heterogeneity, have the courage to try this stuff out. This was a slide that one of my PhD students put together, Wei Chen-Lin, and it kind of captures the kind of more information about those three boxes that I showed you, about the kind of specific details about how each of the different parallel programming models are expressing the nature of control. He did a lot of work in exploring porting different mini apps and applications from one programming model to another. So yeah, do check out Wei Chen-Lin's work. But it captures here, and you can see here on the left-hand side, those are basically the three boxes. How do I access data? How do I define my parallelism? Where's my parallelism? This is all the device control stuff. And it captures the things from there. And we see that things like SYCL and OpenMP both are open standards. Both have very amazing support from Intel in implementing both SYCL and OpenMP. And they provide you all of the controls that you need for explaining where your data and on the parallelism that you need in the system as well. What's great is these are open standards too, right? Which means that many other vendors are also supporting these two things, and many vendors all collaborate together to define what those standards is, right? To standardize the best practice for expressing these things in different ways. OpenMP provides ways of expressing these things using compiler directives that maybe works great for codes like C and Fortran. Does work in C++ too, but maybe it's not so idiomatic. And things like SYCL provide a very modern C++ way of expressing these same things. Again, both are open standards, both cross-industry collaboration, working together to standardize the best practice for expressing and writing performance-portable programs. So that's with these parallel programming models. And what about the languages themselves, right? If I want to write a program, I take a serial language and I make it parallel by bolting on some parallel programming model. But things like C++ and Fortran now, and Fortran for a long time in many ways, are thinking about exploring some of these parallel abstractions directly in the language themselves, right? So we looked here again at just using standard C++ for different parallel algorithms and implementing that same kernel. This is the same results, the same application I'm showing you throughout this presentation. So we implemented these on using standard C++. Those are the bars on the right-hand side, and we're comparing against different parallel programming models there. The great thing is there is a compiler that I can use that gets essentially the same performance using standard C++ as it is with the models that are working on that I might write with, say, OpenMP or something like that. So this is great, right? I can now have some parallelism in the language. If we go back to the previous slide from before, it doesn't give you all of the controls that all of the other parallel programming models might give. Things like OpenMP allow you to have a lot more control, but that's developing over time, right? It takes some time to standardize those things. And C++ for many applications, many straightforward things, it does give you all you need. If you just want to express a big parallel loop, then C++ might be the answer for you. This is the world's most boring graph, right? And this is what makes me very excited about this. Essentially is, no matter what I write my program in, right, it gets great performance on these different GPUs. These are GPUs from AMD, NVIDIA, and Intel. On the right-hand side is the Intel Ponte Vecchio GPU, the 1550. We did this quite naively there. It has a hierarchical structure in some sense, and we just run one kernel off of both the device, which isn't necessarily what you do for best performance. But this basically shows if I wrote this application, this Babel stream in standard C++, I get the same performance. If I wrote it in OpenMP, it's the same performance. And I showed earlier in the previous slides that all of these get great performance on CPUs and GPUs as well. So these parallel programming models really are starting to pave the way for making us be able to have performance portability across these different types of architectures, which is really cool. What about Fortran? The UK is a massive, has a massive code base in Fortran. And we also looked at the standard parallels in Fortran 2 with Deakin current. It's been there for a very long time. There's lots of more recent progress in that space. Essentially, we have the same conclusions as the C++ paper. We have a boring graph in there where everything worked just great too, so that's great. So what am I saying, right? This is the Tin Man, back to our story of the Wizard of Oz. He really loves Fortran. He bought a giant book on it. And Fortran being this high-level language for scientific computing. Really what I'm saying here is that, explore and be happy, write in the languages that you want to write and demand that the vendor supports those things. The languages that you tend to use, things like C++ and Fortran, and the parallel programming models like OpenMP and SYCL, right? They're open standards, they're standardized languages, standardized programming models, and all the vendors support all of these things. So kind of trust your heart and write in the language that you like, and you'll explore these kind of new features. Obviously, we get to the end, right, and there's the guy behind the curtain and the Wizard of Oz. And really, what is enabling all of this stuff to happen? And we're finding that this is LLVM. LLVM is this open source compiler project that supports a whole range of CPUs and GPUs. And with a lot of the recent work with liboffload, previously called libomp target, that supported the OpenMP runtime, we're finding lots and lots of companies are kind of contributing and exploring how we can have a single independent runtime layer that can support all the different CPUs and GPUs. So LLVM really is the enabling technology, which is kind of enabling us to kind of get these results and kind of realize the Tin Man's vision of writing in Fortran for forever. But what do you do now, right? I said C++ and Fortran, they enable you to express very straightforward, simple things, but what if you need the control? So the scarecrow here in our story, he has some really, really complicated code. It's so complicated that the generative AI had to blur it out. What does he do today? He needs to make progress. He needs to use his brain and come up with a solution today, right? You need to get your work done now, as well as follow that path to the future, to Oz, as the new machine is coming online. And really, part of this then is this kind of reality of performance portability is sometimes we do need to specialize. We do need to, when we can't express it in the high-level language of C++ or Fortran, what do we do, right? What do we do next? So I was doing some work with folks at Intel on trying to characterize that metric. And on this graph basically shows like the compass. That's a direction point where the left-hand axis is showing that performance portability. What is my expected performance as I explore different systems? What performance can I expect on average from my code across all the processors that I run it on? That's the y-axis, and the x-axis here is some measure of how different my code is across those different platforms. We use a tool to do that. It's basically a compiler tool for measuring that, but it measures how much specialization in my code. How many pragmas do I have that say, if my system is a CPU, run this kernel. If my system is a GPU, run this kernel. How much different code do I have? Obviously, you aim for the top right. You want to get the best performance across all systems with single source. But the reality is you're somewhere in the top right-hand corner. And these compass directions help track maybe the journey of an application where they add abstractions to remove the specialization and they do optimization to improve the performance. And you always have this tension of moving north. When you're optimizing, maybe needing to specialize is pulling you back to the west. So this is a really interesting way of capturing some of these real challenges. So what about the yellow brick road? Really, this is kind of the moral of the story. And what it means is to get your work done today as you're following the yellow brick road to the future of your compute. We find that it's paved with these open standards, right? It's paved with OpenMP and SYCL, right? You can write your real applications in these open standard parallel programming models. We see that they get great performance across the range of different diverse heterogeneous systems that we get there. And they've set the path, right? They're in the slipstream of things like C++ and Fortran, where they're helping it mutually define each other to get to those things. So we see the future, I think, in my personal opinion, is maybe we can just use C++ and Fortran in the end. But how do we get there? How does that postdoc at the beginning of the story? How does Dorothy get to Oz so she can get her science done? And really, we see it with these open standard parallel programming models. So with that, I'll get to the end of my talk. And if anyone from the audience has a couple of questions, I think we've got a few minutes. Thank you for listening.